Hello, everyone, again. I'm so glad to see you all again here. I know we have some new faces, but also some old ones. Yes, welcome here to this session of the Pari Center's online summer series, exploring the life and work of David Bohm. I'm James Peat Barbieri, member of the Board of Directors of the Pari Center, and I'll be your host for this session. Today with me, I also have Eleanor Peat, who is the program director of the Pari Center. So if you have any questions, just write to us privately or publicly in the chat section in the Zoom call. Before we begin, I just want to remind again the rules for this Zoom call. I know we have a few new faces. So during the presentation, we ask participants to turn off their microphones to ensure a better quality audio. For this reason, we may mute you if we can hear some background noise, but don't worry, it's nothing personal, it's just for audio quality. If you do want to ask a question or make a contribution or anything like that, there is a raise your hand function here on Zoom. If you can't find it, just physically raise your hand, and if I spot you, I'll hand it over to you. We also invite participants to turn on your camera, as we believe seeing everyone's faces makes a nice, inclusive educational environment. I do need to remind everyone that the sessions will be recorded for archival purposes. The recordings will not include the possible breakout room discussions, but it will include the speaker's presentation and the follow-up Q&A and discussion. These recordings are available to anyone who has purchased a ticket for the session, or if they've paid for the session but could not attend, then we can send them the recordings. Today's session will be divided in 3 parts again. The first will have the presentation by our speaker, Dewdney, and then we will have breakout rooms of maybe 4 or 5 people, which will last about 15-20 minutes, which is an opportunity for you guys to sort of discuss what has been talked about. And then we'll come back together in this big room with everyone where we'll have the Q&A and discussion. Now I would like to introduce our speaker, Dewdney. Today we are proud to have with us a mathematician who pioneered the first calculation of quantum trajectories according to the Broglie-Bohm theory for the double slit experiment and quantum tunneling. And through his work helped put the Broglie-Bohm theory center stage in analyzing the foundations of quantum mechanics. Chris is now permanent professor and researcher at Portsmouth University in the UK. Enough of me, over to you, Chris.
Thank you very much for the introduction. There's an awful lot to talk about, but what I thought I would do is really just take the opportunity to give a little more detail about some of the animations that we saw in the wonderful film about David Bohm, which I think has created a lot of interest, and I've heard some very positive comments from all over the place about it. So I'm not going to use any equations today. I don't know how many people are physicists, might be disappointed by that, but I suspect those who aren't physicists will be quite happy about that. So I'll try and just talk about the animations without too much mathematical detail. So what I'm hoping is going to work, and we did talk with Eleanor about this earlier, is to share my screen so that we can look at some of those animations again, and indeed some of them which didn't appear in the film, but were made with the film in mind. So where do you start on this long story? Well, of course, it's always a good idea sometimes a good idea to start at the beginning. So what I thought we could do to start with is really go back to the very beginning of the whole idea that matter, particles actually have wave-like properties. So who do we owe that idea to? Well, that, of course, the idea of Louis de Broglie, who has a name which is quite difficult to pronounce for English people. And in fact, I remember when I went to work with Jean-Pierre Vigier in Paris, who was himself Louis de Broglie's student, he insisted on referring to de Broglie as de Broglie. And I thought, well, this is very strange. And after a while, I said to him, why do you pronounce his name de Broglie? Surely that's not right. And he looked at me and he said, well, you know, I pronounce it like that, so you English people know who I mean. So if I do mispronounce it, then that's, which I undoubtedly do. I won't say de Broglie, I shall make an attempt at least. Anyway, so if we go back to that idea, it's very interesting, you know, that what the orthodox physics community took from Louis de Broglie's original work was really just this idea of the relationship between the momentum and the wavelength of a wave which Louis de Broglie associated with all particles. So his famous P equals H over lambda. Okay, that's an equation. Or lambda equals H over P. You know, that's all you really see in the books about Louis de Broglie. But in fact, when you look back at his thesis, you read his thesis and you see what he was saying about it at the time, and you look at his Nobel Prize acceptance speech. Not many people get a Nobel Prize, I suppose, for their PhD thesis. But when you look at what he said there, then he clearly had this idea that quantum mechanics could be described using particle trajectories. That was the basis, really, of his the way he came to the idea that particles should have wave-like properties. So what he really did was bring together the principle of least action, which was a way of doing classical mechanics, a way of calculating trajectories for particles, and the principle of least time, which was used for calculating paths of light rays. So here we had two principles, one to describe the rays of light or other fields, I suppose, and another to describe the paths of particles. And what Louis de Broglie said was, well, if particles are going to have a wave-like aspect, then their trajectories should be determined by the rays of the associated wave, which he had suggested that all matter should have. So that was in his thesis. That was the way he was thinking about the fact that quantum matter should have wave-like properties. So it wasn't something that was added later after he'd had the idea about, you know, particles should behave in a wave-like way. That was the way he was thinking. But of course, the orthodox physicists of the time threw all that part of it away, the so-called pilot wave idea, and simply concentrated on the fact that, okay, so if we have particles displaying wave-like properties, then first of all, let's go and see if we can measure these. Let's see if we can observe them, which of course they were observed and confirmed. And then they just retained this relationship between the momentum of a particle, that's its mass times its velocity, and the wavelength of the associated wave. And it's a great, in a sense, injustice that Louis de Broglie is just reduced to this one formula when he was really thinking about pilot waves right from the start. Of course, Schrödinger then went on to develop his equation, which enabled the calculation of the behavior of these de Broglie waves, the psi waves as they became known in Schrödinger's equation. So I think that's worth mentioning. And why is it related to David Bohm, what we're talking about? It's because, well, 25 years or more later, David Bohm had come to very similar idea, not through the same route, but he had come to a theory which was in fact had a lot in common with Louis de Broglie's original pilot wave theory. So that's why many people refer to Bohm's theory as the de Broglie-Bohm theory. And I think Bohm himself would not really have liked the Bohmian mechanics, which has become the moniker for it today. So I thought what we'd do is just to use some of the animations to get a bit of a view on this. So I shall now gingerly see if I can just share the screen to show you one of the animations that didn't appear in the film, but I think makes this point about the relationship between the rays and the particles. So I get my QuickTime player. Oh, hang on. Let me share my screen first. Yeah, so this one is the one I want to share. Share screen. Can you see it?
Not just yet.
Okay. Share screen. Oh yes, go press share. Okay, I didn't see that.
There we go.
Okay, so well, what this shows is it's a representation of a wave passing through a barrier, and we'll note that at this time the gap in the barrier is much wider than the wavelength of the wave, which is simply the distance between the peaks. And we'll see that the wave just passes through the barrier. We also see some particle trajectories. And if I just stop it at this point, let's just go back a little bit. So here we see particle trajectories. They pass through the barrier. And if these were classical particles, they pass through the gap. They're not affected by the gap. The walls of the gap are distant from them, so they just travel in a straight line. And that would be the case for classical particles, even as we make the gap narrower. But according to the wave theory, as we make the gap narrower, there's a diffraction of the wave, there's a spreading out of the wave around the corners. This wave effect, for instance, accounts for the fact that you can hear around corners because the sound waves diffract around the corners. The classical particles would carry straight on, but if we take Louis de Broglie's idea that these particles now associated with this quantum wave, we see this as a quantum wave, then follow the rays of the wave, it's very, very simple. All that happens is that particles, instead of following the straight lines that Newton had predicted, they simply always travel in a way which keeps them going perpendicular or at right angles to the wave fronts. So we can see, say, take the crests of the waves. So then as the wave begins to diffract, so the particles themselves start to move in non-straight lines. So now we see the slit is about the same size as the wavelength of the wave. The wave is spreading out, and the particles, if you'll notice, are following lines which are at right angles to the wave. And when I tell my quantum mechanics class that that is how you understand quantum mechanics, that's they are in a way quite shocked, and they say, well, why do we hear all this other stuff then? If it's that simple, it just seems obvious, when you make that idea. But back in 1927, Einstein, what motivated this particular animation was that Einstein had proposed the thought experiment way before, in 27, way before his more famous EPR experiment. And what his problem with this was to say, well, let's imagine we have a bank of particle detectors that can record the arrival of one particle at a time. And then we calculate according to quantum mechanics what should happen. So the first thing you have to do in order to calculate this according to quantum mechanics is have a wave function included for each one of these detectors. So you've immediately gone to a much more complicated description, which goes beyond ordinary space. We'll talk more about that later. But what Einstein's problem was that if you take the Bohm view, it's patently obvious why the particle, why one of the detectors fires and the others don't. It's because the particle actually goes to one of them and none of the others. But what quantum mechanics predicts is that there's a probability for each of these detectors to detect the single particle. Only one can do it, only one can receive the particle. They all have a probability of doing so. In fact, in this particular shot, the intensity of the beam here is shown, well, as an intensity of the light. And where it's brightest is where the probability is the highest. So what was Einstein's problem? He says, well, how can we account for the fact, just using ordinary quantum mechanics, that one of these detectors fires and all the others don't? So as soon as one fires, all of the other detectors have to know that they must not fire, they cannot fire, even though they have a probability to do so. And this has become discussed over the years in terms of the non-locality of a single particle. So somehow all those other detectors, in this particular case, it's this one, which has happened, all of these can no longer detect the particle, even though there is a small or some finite probability that they could. So in the orthodox view, there's no explanation for that. We cannot have an explanation for why one of these detectors fires and none of the others do. In the orthodox view, which one of the detectors fires is a purely random event. There is no possibility of explaining this at all. And Bohr famously said, you know, all sorts of things like there's no quantum world, there's no possible way of conceiving of what happens in the quantum world. We can't analyze the quantum world at all. We can just talk about the results of experiments, which is the probability or the number of times this detector fires compared to the number of times the other detectors fire. So this, in a sense, you know, Einstein's first thought experiment on this topic, you know, contains a good description of, you know, what are the problems. But the thing that strikes me for this is that, look, had history been the other way and people had taken Louis de Broglie and then David Bohm seriously, and the whole world had spent the intervening 100 years calculating particle trajectories, and then somebody came along and said, oh no, we don't need those particle trajectories, they shouldn't exist, we'll get rid of them. What you get is mystery. So David Bohm's view, perfectly clear explanation in terms of well-defined motions. The orthodox view, where we immediately have all those problems of wave packet collapse and interpretation. In fact, we can't even get a definite world in the normal interpretation. We need to explain why one of these detectors fires and the others don't. And of course, the wave function for all the detectors that don't fire has to collapse to zero. The probability has to go to zero when one of these detectors gets the particle. And that, of course, is the famous collapse of the wave function. So that was one of the animations that I thought, you know, gives quite a nice view of this. And this idea that the particles follow the normals to the wavefronts, they always move at right angles to the wavefronts, is a very, very simple idea. And in fact, many physicists who actually support this sort of approach, namely Goldstein and the like, say that's all you need. So want to move on now to think about what happened, as history developed. So given that everyone had more or less rejected de Broglie's view, even though that was the foundation of quantum theory, the orthodox interpretation of Heisenberg and Bohr held sway for many years. And then we heard yesterday about how Bohm came along in 1952 and made his proposal, which I said was related to Louis de Broglie's. And we heard how that was not taken on board by the physics community, either in America or in Europe. That's still a bit of a mystery as to why that was. So lots of reasons, I think, as to why Bohm wasn't taken seriously in 52. So again, after the publication of that paper, these ideas went back into the wilderness. Nobody was talking about them. In fact, even when I went to Birkbeck, having studied physics and philosophy at Warwick, and then I actually wrote a dissertation on Niels Bohr when I was doing postgraduate work at Cambridge, so I was pretty much impressed with Niels Bohr at that time. I wanted to do a PhD, and I'd read a little bit about Bohm, but really nothing about his 52 theory. But I thought this would be a good place to go and do a PhD, so I wrote, as David Bohm was clearly someone who was a physicist and philosopher, so I thought that would suit me rather well. In fact, I was intending to write a more sort of philosophical PhD than the one I ended up with. So I went along there. Nobody was discussing theory, and as you've heard in the film and various books, I came across this 52 theory while browsing in the bookshop across the road from Birkbeck College. Belinfante's excellent book there, Survey of Hidden Variable Theory, and he had this whole chapter on what he called Bohm's 51 theory. And so we went to see Basil, the two Chris's, as Basil calls us, Chris Philippides and myself. And we said, well, how come nobody's talking about this? And well, you've seen in the film about that. But we proceeded to make the calculations of the two slit experiments. And I'm going to talk a little bit more about those. Oh, incidentally, when I wrote to Birkbeck and wrote to David Bohm, I got a very nice letter back from Basil, actually, who said that Bohm wasn't taking PhD students at that point, but he was very happy to take me on. And so I was very grateful and indeed became Basil's PhD student in Bohm's group. So we did the two slit calculations, and then I'm going to tell this the other way, slightly the other way around, because then after we'd done that, Basil took me down into the basement of Birkbeck College and showed me these little film loops which showed wave packet scattering from square potentials. And he said, do you think you could do the Bohm version of that? And I thought, well, I'll have a go. So that indeed is, after sort of weeks of punching cards. In those days when you did computing, you had to sit at a typewriter or punch card machine and punch the cards. You'd end up with a wad of cards, which you then gave to the computer operator the night before. They'd run it overnight, and you go back in the morning, there would be this elephant toilet roll, they used to refer to it as, this printout from the computer, which would print your program out and said, oh, you've missed a comma on line 3. So you'd have to get that card out and edit it. And anyway, after all this process, I was able to solve that. And they are the film, the images you see in the film. And I'll just show one of those at this point. We can talk a little bit about that. So I'll try the screen sharing again. See if I can do it the right way around. Share screen. That's one. Okay, so here we have, let's bring it back to the beginning in a minute. So this describes the quantum effect of quantum tunneling. And what we see here, I'll just pause it a minute, is here's the a wave packet that is showing the probability density. So where this is high, there's a high probability to find the particle. So the particle is located, according to ordinary quantum theory and the Born interpretation, in here somewhere. Okay. In Bohm's theory, we know where the particle is. So these snowflakes up here show a set of possible motions. There's only one particle here at the time. So it could be any one of these, but there's only one. Here's a classical potential. So in this region, there's a force. And if the particle, with its energy here shown vertically in the screen, if the particle is below this barrier, then according to classical physics, it should just bounce back. But when you do the quantum calculation, there's some probability that the particle will go through the barrier, even though it doesn't have enough energy. So there's this region in space which is inaccessible to a classical particle, so they all have to stay on this side. But when we do the quantum experiments, and this is the basis of so many bits of technology today, that it's absolutely inconvertible. Well, in fact, the tunneling itself is such an important quantum effect that you know, plays a role in the existence of life itself. And without it, yeah, hardly anything could exist. So the problem was, how do we see what happens in the Bohm theory? So you have to make a numerical integration of the Schrödinger equation, and then use the wave function you get from that to calculate the trajectories. And just at this time, in the University of London, the University of London Computer Centre was very advanced, and it had this capability to produce computer animated films. And so when I discovered that, I thought, well, wow, this would be absolutely marvelous. And I used to then send off the programs, and what I would then get back was a film canister with these films in, which I then had to rush around to find a projector so I could see what I thought was coming out was actually coming out. So it was a much more involved process in terms of actually looking at the results, but they were, after various false starts, of course, they came out to be rather impressive. And during this whole process, they switched to color. So I thought I'd show you the color one, which was made rather later than the ones that we saw in the film. But you see here, this quantum tunneling, the point about this is the fact that there is a clear motion, there's a well-defined motion of the particles. This red stuff here is the quantum potential, which is controlling everything which happens here. So just like in the two-slit experiment, where there's a deep valley in the quantum potential, the particles go across very quickly, and where there's a plateau, they slow down. So in this particular case, the incoming particles, when you calculate according to quantum mechanics, have some small probability that they will tunnel through, something which is absolutely forbidden in classical physics. So when you fire a particle at one of these barriers, all quantum theory can predict for you is a probability that it will be transmitted through and a probability that it will be reflected back. There's no story, there's no trajectories in ordinary quantum theory. All we have is the probability. So when in fact you find that in a particular case, a single particle, say, has gone through, then according to the orthodox theory, that is something you can't possibly explain why you found the particle to be there, and no trajectories, no analysis. And this, of course, is the theory, the approach to quantum mechanics that has been taught, well, I guess for almost 100 years, things are changing slightly, but not so much. It's still thought that quantum theory is inherently a random theory, and there's no explanation for why things happen. And of course, you could imagine putting a cat over here, for example, and if the particle goes through, it kills the cat. And if it reflects back, the cat stays alive. All quantum theory can predict for you is the fact that at the end of the process, there'll be a probability that the cat is dead, or whatever less hazardous thing you want to happen to the cat, or it stays alive. And the famous Schrödinger cat can be seen just very much in this example. But the key thing is that, you know, in Bohm's theory, that whether the cat is going to be alive or dead at the end of the experiment is already determined at the beginning of the experiment. It's determined by which one of these possible particle motions is the actual one. So what the particle actually respond to is the quantum potential. Okay, so it's the quantum potential which determines in Bohm's theory how the particles move. So this very fundamental quantum effect gets a very clear explanation in Bohm's theory. Okay, so let's move on and actually go back a little bit in time and have a look at some of the other animations which were produced. So in the film, the first one we see is the double slit according to the Copenhagen interpretation. So I don't know if can you hear the music? I'm not sure how to turn that off, so I hope you can still hear me. So if we just have a quick look at this, we've seen already what happens to a wave as it goes through a slit. It spreads out. If you've got two slits, the waves spread out and they spread into each other. And according to wave theory, they interfere and produce these bands of light and dark. So in quantum theory, where the pattern is very bright, is where there's a high probability of finding the particle, and where it's very dark, there's very low probability of finding the particle. But of course, there are no trajectories. All we see, in fact, are the spots on the screen, which we saw at the beginning. So this is shown very nicely in the film, I think. It's rather artistic rather than being scientific, but it shows very nicely the interference pattern. At this point, what happens is that there's a detector introduced. We can imagine a detector placed here. In fact, we'll see it shortly. And what the detector does is it enables us to know through which slit an individual particle passes. And notice what's happened to the pattern. Once we know that the pattern has, the interference has disappeared, and we now just have the straight sum of the beams coming through these two, and we see the spots occurring on the screen where the particles arrive, and these are now spread out in a different way. So Feynman said there's a very nice video which you can find on the YouTube of Feynman talking about the two-slit experiment. And at the end here, he talks about this possibility of putting a device in to determine through which slit the particle goes. And I think this is virtually the only mention I've ever seen of hidden variables from Feynman. And he says it's this very fact that when you put the device there, it changes the pattern. that prevents any possibility to have a hidden variable theory. That's at the end of his video. But of course, as we also know, if we have a look again at the other thing that we saw in the film, if I can just find it. So we see a repeat of the, hang on, I think I'm showing the same one. Sorry, that's the wrong one. It should be this one. So in Bohm's theory, the particles pass through one slit or the other, follow definite trajectories, and go to the bright parts of the screen. And I love this particular animation. It's one I dreamed about for years, of actually being able to follow the particle and watch it in 3D, zooming over this quantum potential surface. So it was an absolute pleasure to work with Colleen in Romania and produce these wonderful updated versions. So what's interesting about that in particular is we think about what is determining the way the particle moves is that quantum potential which acts locally on the particle, but it actually has information about the whole experimental setup. So the way the particle moves depends on the whole experimental setup, whether there's a detector there, whether there's one slit open or two slits open. So the two slit experiment, of course, the iconic experiment in the interpretation of quantum theory, actually shows us, when we look at Bohm's approach, the wholeness expressed in quantum theory, namely at the location of the particle, it's responding to its whole environment. Okay, so there's a unity between the environment and the motion of the particles. This is one aspect of quantum wholeness. Okay, so let's have a look at another recording which shows this. Let's just find the right one. Is this one we just looked at? Oh, yes, yeah, okay. All right, so that's not the one which has the, what happens when the quantum potential comes in. Let me try another one. Stop that one. And sorry about this. Hopefully this is the right one. I know it's just the same one. Sorry, I think I've seem to have the wrong video there. Just give me a moment to have a look at where that has gone.
Let me know if you need any help, Chris.
Oh yeah, okay, because I have sent these through. Let me just check this one. Oh yeah, okay. Right, now I've found it. Now I just have to share it somehow. Okay, so now you see the detector in place here. It's not switched on at the moment, but when we switch it on, that's just happened there, you'll notice pattern changes, the interference goes away, particle paths are now not wiggling around, they're moving just as they would from a single slit. So when the detector's sitting here saying, oh, the particle went this way or the particle went this way, the slits behave, the particles coming through this slit just behaves as if the other slit wasn't there. So we still see these motions in real space as the detector fires. But you know, the explanation for this in quantum theory is really quite staggering as to why the interference disappears. And for me, it's, you know, one of the most significant aspects of quantum theory. And it really underlies the fact that we cannot give an explanation of why the interference disappears if we limit ourselves to motions in real space. If all our concepts have to be formed by behavior in real space, the space of our everyday, then it's not possible to understand this. We need to, this experiment, when you introduce the detector, we have to introduce a wave function for the detector. And that's represented, so there's a coordinate, if you like, for the detector as well. And in this box up here, what we're seeing now is the this is called configuration space. It's actually the fundamental space of quantum theory in Schrödinger's version. Okay, it's very easy to get lulled into a false sense of security. In fact, I was doing it really myself at the beginning, saying, look, it's just the particles following the rays of the waves in real space. But actually everything in quantum mechanics is really, in Schrödinger's theory, is really happening in the configuration space. It's a space that goes beyond everyday space. It's an abstract, if you like, an abstract mathematical space in theory, but one might say it's indicating to us that there is something beyond our everyday space and the interactions and relationships in everyday space. Is showing us that, because we cannot make a picture which just has relations in everyday space, interactions in everyday space, which can explain why this goes away. But in the configuration space, as we see the detector operating, its coordinate either moves downwards or it moves upwards in the configuration space. And as it does so, it's separating the wave in the configuration space from the right slit from the wave in the left slit. So if this detector wasn't there, these would collapse down onto each other and they would interfere again. But what the detector's doing in the real space is that it's pulling these apart in the configuration space. So now the rays from this slit don't touch the rays from the other slit. And that's what the detector does in this more in the space of quantum mechanics. And I think that's, you know, really indicating to us that we need to move beyond ideas in everyday space and time. And perhaps this is an indication that there are some deeper processes going on, which of course Bohm and Hiley have been attempting to develop. So this is really how the world is. It's a configuration space in which the motions take place of everything. And so you could say that the universe itself, there is one universal wave function which describes everything in the universe in a huge, 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 complex, multi-dimensional space. And as the universe evolves along, its wave function will evolve in various ways, and if measurements are made or things happen, it will divide up into channels, and there'll be different probabilities for all these channels to get all these possibilities. existing in the quantum wave function. And of course, in the many worlds theory, they just say, well, of course, that's right, and they all exist, and they all exist at once. There's multiple universes, all existing at once. But Bohm's view is rather different. It says, yes, there is this wave function in this configuration space. It's the only way we can really describe correctly what's happening. But only one, there's a path through this configuration space. There's an actual path that the universe actually takes. And this wave function of the universe, of course, because it's in this configuration space, what we find is it doesn't really matter if objects are close together in our everyday space or not. What counts is their relationship in the configuration space. So you can have a particle on Andromeda, and you can have a particle on Earth. In ordinary classical physics, we'd say there's no possible way they could influence each other apart from over, I forget how many million years it would take a signal to get there. There's no way, but in quantum mechanics, we see that, as we'll see in the next animation, this is possible. So it tells us, I think what this is probably, for me, the most significant thing about quantum mechanics is that you cannot formulate this theory in real space. The Schrödinger equation is telling us we need to go beyond this configuration space wave function. Is really telling us that what is going on cannot be accounted for in our everyday space and time. Instead, we have to countenance this idea that the reality is not what we see every day. You can't formulate it in that space. We have to make this formulation in this much more complex space. And really that, shows you how the whole universe can be one whole. We often hear this, that Bohm talked about wholeness. Well, there's one universal wave function. So everything in the universe is playing its part in how that wave function develops. It may be that, some parts of the wave function become relatively free of what's happening in other parts of the wave function. But this is, I think, for me, and of course, this means non-locality. So if we calculate what happens, as I say, to the particle on Andromeda and the one on Earth, we find that they can be correlated even though no signal passes between them, because what's really happening is determined in this more abstract space and not in our real space. Okay, so was I sharing the screen during all that? Not. No. Okay, so what I'd like to do really is to just have a look at, before we go to the breakout, just the actual experiments, the first experiments which were done after Einstein proposed his the EPR experiment. Bohm, of course, in his quantum theory textbook, which is an absolutely wonderful book. I don't have to tell anybody here that, no doubt. It's one of the best explanations of quantum theory, and it's one that I was very happy to find, because there's a lot more discussion and explanation, and you get a much better understanding from that book. It's not just about, can you do the questions at the end of the chapter? It's about, can you understand this theory, what's going on? Anyway, famously, he reformulated the EPR problem in terms of spin, and of course, spin and polarization have very similar quantum mechanics. So that enabled the actual experiments to take place, which then confirmed all this. So let's just have a look at, first of all, let's just have a quick look at the particle spin. Oh, wrong one. Sorry, I've got to find the right screen here. Where is it? There we go. Yeah, so I'll just say a little bit about this. We see two particles in this animation, but again, what we're seeing is two possible motions of a single particle. Okay, and what we can measure this property called spin using these things called Stern-Gerlach magnets. No need to go into the physics of that. What happens is that whenever you measure this property called spin of a particle, you either find it's plus a half if it's an electron, or minus a half. So it either goes up or it goes down when it passes through this magnetic field. In ordinary quantum theory, when you send a particle through, if it starts with a spin component, say pointing horizontally across here, there's a 50% chance that it will be found to move upwards in the field and a 50% chance to move downwards in the field. And that's all the quantum theory can tell you. There's a probability. And as I've said many times, the orthodox theory would say, and there's no possibility of explaining why the particle ends up in one place rather than another. When I was doing these calculations, actually, I was already moved on from Birkbeck to work in Paris. And I remember Jean-Pierre Vigier had come over, and he was talking with Basil after a seminar. He was talking with Basil in Basil's room, and I was over in the PhD students' room. And Basil came in and said, "Oh, Jean-Pierre would like to have a word with you." So I went in, and Jean-Pierre said, "Well, how would you like to come and work in Paris?" And I was quite taken aback. I had exchanged a few letters with Jean-Pierre Vigier, but I was quite surprised by that. And by that time, I already had 2 children. And so my first thought was, oh, that would be great, but I don't think I'm going to be able to do it because we've got the children, and we're living in London. And so I cycled home from Birkbeck 8 miles over Crystal Palace Hill, thinking about all of this as I cycled home. And when I got home, I opened the front door, and my wife was there, and I said, "You know, we're going to Paris." and so we did. And that's where I did this work on the spin measurement problem and the EPR problem. And these animations are, again, updated versions of the calculations that I did. The way we did it, in fact, in this animation was that I gave to Colleen, the animator, who's a wonderful animator, actually. He's a real, number one, he could understand, I think, enough quite quickly to get what was going on. And then he was able to create these magnets. I think magnets took him, I don't know, a few minutes to draw up on his wonderful software. So these, as I say, are updated versions, rather lovely versions of those original calculations. But what happens in Bohm's theory when we do this measurement is very straightforward, actually. If we look at these 2 possible motions, this one and this one, what we notice is that this one is above the center line, this one is below the center line. And what determines in Bohm's theory whether this particle is going to become a spin-up particle or a spin-down particle is simply its initial position in its wave function. So this theory is deterministic. Everything that's going to happen is known from the start. And I guess if you apply that to the whole universe, you could say everything that's going to happen in the universe is already known from the start. If we say that all that there is the Schrödinger wave function evolving in time, there's a definite set of coordinates where the universe starts, it will follow this path. So we end up almost in a sort of Laplace's demon situation again, because we have determinism in this theory. Yeah, so we see this particle spin is explained very straightforwardly. Now, the EPR experiment in Bohm's formulation has two particles. These, remember, were just showing us two individual possible trajectories. But in Bohm's version of the EPR experiment, there are two particles which are in an entangled state, which means that neither particle has its own wave function. Only together as a whole do they have a wave function. And it's this whole wave function, again, the nature of wholeness reveals itself very much with entangled wave functions. These entangled wave functions have to exist in configuration space, make no sense in ordinary space. But when you have these entangled wave functions, then we get these non-local correlations, which are totally independent of where these particles are in real space. So let's have a look at perhaps I won't show the other 25 animations which I've got here. It could be here for a long time. So perhaps we'll just have a look at, right, if I can find it, this one, yeah. So if let me close this window and I won't get confused. Okay, so I mean, here's a rather nice representation of this. It's obviously it's trying to show that these two devices, these two Stern-Gerlach devices, are separated by as much space as you like. Okay, so this bit in the middle is just representing the distance perhaps between Andromeda and the Earth. And these are just the entrance slits where the particles must pass through to collimate the beam, so that when they go through the Stern-Gerlach devices, they will have their spins measured. Now, in Bohm's theory, well, of course, I think this gets sometimes misinterpreted, because John Bell showed that the correlations which exist between the measurements which take place here and the measurements which take place over here, over on Andromeda, the correlations which we see and have been confirmed so many times cannot be explained but by local hidden variable theory, right? No, what he showed was no local hidden variable theory can explain these correlations. And in fact, John Bell came to his theorem, I think, by studying Bohm's theory, seeing the non-locality, which was very evident in Bohm's theory, and asking himself the question, would all hidden variable theories have to have this non-local character? And that's, I think, how he came to his very famous theorem. But it's worth emphasizing again, I think, that it only rules out local hidden variable theories. And of course, these so-called no-go theorems, these impossibility proofs, I think played quite a role in the fact that Bohm's theory was not taken seriously, of course, because von Neumann also famously had a proof that hidden variable theories were not possible. But again, he made some assumptions which are violated in Bohm's theory. In fact, funnily enough, in Bohm's book, he even has an argument that hidden variable theories, in his quantum theory book, has an argument that hidden variable theories can't exist, and then promptly went on to make one, so just disproving himself. So I think I won't talk so much perhaps about this because I see time is passing as usual quite quickly. Just to say that these two particles are setting off from some point in space, say halfway between Andromeda and Earth. They're created in this entangled state. One travels over to Earth, the other travels over to Andromeda. We then take a series of measurements over here and a series of measurements over here. We must do this also by rotating the magnets, but I just show in the animation the magnets orientated in the same way. And what the theory predicts is that this is a total spin zero state, that if this one becomes spin plus a half, this one must become spin minus a half. And Bohm's theory, when I worked all this out, I used the theory we heard about Chiomno yesterday from Olival, because Bohm developed his theory of the spin while he was in Brazil, in fact, with Chiomno and Schiller, two physicists he collaborated with in Brazil. And I think probably the spin theory had been almost more ignored than Bohm's original 1952 theory. But when I came across it, I realized, well, okay, we've done those calculations for the straightforward Bohm's theory of particle motion. So let's see if we can do it for the spin case as well, which took a little more computing, a little more thought about how to do it. But indeed, it worked out. And I remember at the time, I almost became addicted to these calculations. Almost any quantum effect which I came across, I thought, well, let's see how that works out in Bohm's theory. And it was quite an addiction, really, working all these things out. And I think nowadays, many, many people, there's a small industry of people doing these calculations. But at the time, I was working on these with my collaborators. So these were published with Peat Holland and Tassos Kyprianides. Nobody else was working on this spin stuff at all. So let me just say what is one of the most staggering things about this. The first of all is that, if this particle goes up, this particle over here has to go down. How does this particle over here know it has to go down when this particle goes up? It is non-locally connected to the other particle. So what happens, say, to this particle here, doesn't just depend on what's happening here, it depends on what's happening on Andromeda as well. In fact, there's a very simple little thing which I spotted when I did the calculations, which is that, again, everything is determined from the outset. And if this particle, when it enters its slit, is above this particle, relatively speaking, then this one becomes an up and this one becomes a down. It's a little bit tricky to see on this. But the key point is that what happens here when this particle starts to go down, that depends not just on where it is, it depends on where the other one is as well. So there's this dependence of the positions of the particles on the outcomes. But there's an even more staggering effect on this, which is that if we consider the case that the particles are being measured, but then we turn off one of the detectors, this particle will then not be affected at all by the magnetic field. It would just pass straight along there through the magnetic field. Its spin, however, it's a little bit difficult to see this in the calculation, but this little red, I don't know if you can see that on your screen, so this little red thing sticking up here is showing which way the spin of that particle is. So it actually has no spin when it's in here. When it emerges from the field, it develops that spin up. But what is important here is that and this is the last thing I'll say if you're flagging a little bit on this, is that when we turn off that detector on Earth, just a choice whether we flip the switch or not can change what happens on Andromeda immediately. Trying to avoid the word instantaneously there. In a non-relativistic theory, we can say it occurs instantaneously. This is a non-relativistic theory. So you imagine the operator on Earth decide, oh, I think I'll switch my magnet off, and then the particle on Andromeda says, oh, right, I need to go the other way. I was going to be an up particle, but now I better be a down particle. And you might think, well, isn't that a way then we can just communicate instantaneously over any arbitrary distances? And the answer is, well, no, that you can't use it for communication because you didn't know which way that particle was going to go anyway. So if it goes down, it doesn't give you any information because you didn't know it was previously going to be an up particle. So you can't communicate with this stuff. But it doesn't take away from the fact that when wave functions are entangled, that motions are correlated. And in the configuration space of the system, which you have to calculate all this motion in, this abstract space beyond our real space, everything happens actually in that space locally. There's only one path in that space. That one path represents all of the systems which are taking part in the entanglement, could be the whole universe. And there's no way of describing what happens, telling a story which only uses ordinary space. So this wholeness plays out with these particle trajectories because they are coming from the whole wave function of your whole system, whether it be two particles or indeed the whole universe. And so whether objects are in proximity in real space doesn't necessarily tell us whether they can interact, whether they're related or not, or correlated, which is actually, when you think about it, quite a staggering thing, that particles or objects, whatever, can be separated by millions of light years, as much as you like, and yet they are in contact. They are really part of one system. And you could say, well, many people have said, in fact, this is, a version of Bohr's wholeness. But for me, I think, after all these years of doing all these calculations and thinking about it, I think this, the wholeness and the entanglement and the fact that we have to go beyond our descriptions in everyday space is really the most staggering thing. And to be quite honest, I don't really understand it after all these years. So I wouldn't claim to understand it, but it's certainly telling us that there is something going on beyond our ordinary space and time. And, this is what Bohm and Hiley have been edging towards, I think, ever since the beginning. And certainly since the 1952 theory came back into favor with some people, well, Bohm himself, how we could understand this wholeness, this non-locality, has been, the lifelong quest of Bohm, and then carried on valiantly by Basil. So, I mean, as I say, it's been quite a long time, so I think I better shut up. It's always hard to. It's one thing physicists like to do is talk about physics. So it's hard to stop them once they get going. So I will stop there, and I'm sure you will need a break. So let's move on to the next bit.
Oh, well, thank you so much, Chris. Your animations and explanations really did help me, of course, I'm assuming everyone else try to understand all these very difficult concepts. So I do really thank you for this. I guess now we move on to our breakout rooms. I know, Chris, you did send us a question that we could discuss, which is, if quantum physics had turned out to have a perfectly local explanation at the deeper level, would Bohm still have developed his ideas of wholeness and the implicate order? I will attach it in the comment section so you all see it. But of course, you can also discuss, you know, the animations or what the presentation was about. So yes, I'll leave it over to you guys to discuss now.
So I was really wondering about, you know, the link between Bohm's physics and his wider ideas, really. Yeah. And I was trying to think of a question. I thought, well, say physics had turned out differently. You know, how would Bohm's thought of being different?
Yes. Yeah. Okay.
Okay.
Well, yeah, I'll leave it to you guys then. Enjoy. So basically, we've seen through your animations that the detector basically changes the configuration space so that the two wave functions don't interfere because they're two different planes. But in the Copenhagen interpretation, it's basically the conscious observer that causes the collapse of the wave function. So where is the observer or consciousness in Bohm's interpretation? Oh, you're just muted. I'll just unmute you.
Okay.
There.
Yeah, well, you know, if you take Bohm's 52 theory at face value, you just take it as a theory of the evolution of this configuration space wave function, which determines how the whole universe evolves. Then, you know, if there are observers in the universe, then they would be part of this wave function as well. I mean, we would have a wave function. We'd be part of this wave function. And, you know, if you take it literally, then, as I said earlier, that the whole evolution of the universe is determined right at the outset. So there really is no scope for consciousness. You know, that would, I mean, obviously David was very interested in consciousness. But I think he would say, and I think I heard him say something like, well, you know, the electron is responding to information through the quantum potential. Okay, there's the quantum potential is encoding information about the whole environment of relevance to that particle. So it takes in information, it responds to that information by moving in a particular way. And he, you know, well, isn't that what we do in our consciousness? You know, we take in information, we process that information, and we behave perhaps differently as a result of that. So I think that probably for David, consciousness was something which was very widely distributed, and it wasn't something magical that was given to us at some point in our evolution. That there are elements of consciousness throughout the whole chain of being, I suppose, from electrons up to complex objects like ourselves. But there's no real role for the observer, okay, in this. We don't need an observer's consciousness to collapse wave functions and to make things definite. Things are definite because they are definite. There's a definite trajectory, and the observer then takes part of the, you know, the observer is then also part of the story, but not in the sense that you need an observer to collapse the wave function. The observer is then part of a quantum system, but without having any fundamental role. I mean, some of the school of physicists who started to name Bohmian mechanics, Goldstein and so on. They like to have, I think they wrote a book and like to have conferences, quantum physics without philosophy. And we don't need the observer, we don't need consciousness, we don't need any of that stuff. It's just physics. Yeah.
Great.
So you're absolutely right. There's no collapse, and Bohm doesn't need an observer to do it.
Great. Well, thank you for answering that question. We actually have a sort of a follow-up. It's in that line of thinking. A question from Arjan. I think that's how it's pronounced. I don't know. Would you like to ask that question that you asked in the comment section?
Sure. So if there's a single underlying wave function that gives us determinism, then what happens to individual choice in kind of the 3D space that we're aware of?
Yeah, so, this is a bit like the same question that we have with classical mechanics, really. And Laplace puzzled about this because Newtonian mechanics is completely deterministic. And so he argued that if we knew the position and momentum of every particle in the universe at any particular time, and because the theory is deterministic, we would know the whole future and the whole past, because we can just turn the handles on Newton's equations and we'll see how the future unfolds and how the past must have been, because it's a deterministic theory. And on one level, if we had the wave function of the whole universe, that would include everybody in the universe, everything in the universe, including ourselves, and that would all evolve. So it's just in a deterministic way. So it would be, we kind of would have Laplace's problem back, in the sense that, how you understand consciousness and the influence of consciousness on the behavior of matter is something I think that would require us to go beyond this Schrödinger theory and the evolution of the wave functioning configuration space. You need to, you need to have a deeper understanding. And I think that the whole question of information is obviously very important today. And, I think that is perhaps something that is missing from physics, that we don't really have theories which tell us about the importance of information and how information itself can have a causal influence. And I think sometimes when I'm musing on these things that, that might be the next big change, or it will be a big change in physics when we understand the role of information on all levels in determining how things happen. So I talked quite happily in the when I was talking about the clips from the film about an individual deciding or not whether to flick the switch on the Stern Gerlach. But of course, if you take it literally, then that would already have been decided. So, we kind of have the same problems if we stick just straight to the state, the very straightforward Schrödinger theory and the Bohm version of that, same problems with consciousness as we have in classical physics.
Well, yeah, thank you, Chris, and thank you, Arjun, for asking that question. I believe, Basil, you wanted to add to that?
Yeah, I'm going to be outrageous.
Surely not.
Basil, not Basil.
There is no wave function.
Okay.
Well,
the trouble is, having said that, I presume I now have to explain what I mean.
Just a bit, yes, please.
Just a little bit. Well, if you look at the way we got into quantum theory in the first place, that means going back to the 1920s and 30s, what one found was that it was essentially an algebraic approach that Heisenberg introduced. He talked about it as matrix mechanics. Now, I suppose all you guys know about the Matrix because there was a film made of it, wasn't there? But so the idea there was that you didn't have the Schrödinger equation as such. You had the Heisenberg's equations of motion. Now, we've been told that they are equivalent, the Heisenberg picture and the Schrödinger picture. You've got to be very careful of what we mean by equivalent. One can show mathematically they are equivalent, but are they physically equivalent? And what you find is that they are not physically equivalent. And what the algebraic structure produces is something which is called, sorry folks, a non-commutative geometry. That means the geometry is very different from the Euclidean geometry, from the Riemannian geometry, and so on. And one of the things that has been developed just recently is getting a good insight into what this algebraic geometry is. And within that, the process itself is actually described by the algebraic geometry. And you don't need to have a wave function. All the information that we get out of the wave function actually comes from the dynamical algebra itself. And you don't get into these problems, you get into a lot of other problems, but you don't get into this particular problem if you go down that route. And that's called algebraic quantum mechanics. And I will say a little bit about it when I talk.
Right.
Yeah.
That's the reason for me being outrageous.
Yeah, I think that's fair enough. We wouldn't expect anything else. But, you know, and what you say is of course, absolutely right. There's always been the alternative approach to quantum mechanics right from the start. And one would want to, you know, recover the Schrödinger story within that. But, and what you, in recovering the Schrödinger story, I think you would gain insight into, you know, what might lie beyond this configuration space story. You know, where does that come from? And, you know, that I think is very important and quite fascinating, and even more abstract.
Can I just make a quick comment?
Yeah, go ahead.
It's Paul Howard here, yeah. Basil, in the film, I think if I'm quoting you correctly, you said that with the quantum potential, you explain the qualities that give rise to the interference pattern without the need for a wave function. Am I sort of quoting you?
No, that would be a correct quotation.
So in a sense, what we're saying is that Bohm took a different route. He wasn't necessarily trying to solve the wave function collapse problem. Would that be correct?
Yeah, I don't think it's a real problem. It's a pseudo problem. We have been cracking our heads, and I say we, all the physicists from little me to big Feynman, Einstein, you name it, have been trying to solve the collapse of the wave function. And over nearly 100 years, and it still has not been solved. Now, does that, for me, that means there's something wrong somewhere. Because by now, with all our experimental techniques so that we can go and explore these mathematical ideas in the laboratory, we still are faced with this problem. It's a problem which was introduced by von Neumann in his classic book in 1930. And if you, can I stay a little bit more? People interested me in saying a little bit more?
I am, yeah, go ahead.
Yeah.
I do want to give a space to other questions as well, but yeah, sure,
Please
go ahead.
Stop me as soon as you think I'm going too far.
Okay.
But the point is that von Neumann actually changed his mind about the wave function. I don't know whether people realize that. He wrote a letter to Birkhoff in 1935-36 saying, I am going to say something which you might think is heretical. I no longer believe in the wave function. And he then outlines why he doesn't believe in it anymore. It's not very clear, so you have to dig deep. So I went back and had a look at what is known as the Stone-von Neumann theorem, which tells us that the Schrödinger picture is unique, but as a rider up to a unitary transformation. In order to prove that, he had to go outside the Schrödinger picture to a larger algebra, and that larger algebra is now called the Moyal algebra. And in that, using that Moyal algebra, he showed the equivalence. But the Moyal algebra is a non-commutative algebra, and it is bigger than one has in the Schrödinger picture. So when you're talking in terms of the Schrödinger picture, you're only talking in a partial view. There is something much deeper that we can lay our hands on in what we would call the Heisenberg algebra. But that has to be brought out in a clearer way with some concepts and a little bit more discussion. But that's the reason why I'm making this claim.
Yeah, if I could just say, you know, that's what you say is of course correct and historically correct. And often when giving talks on Bohm theory, you often hear that people will say, oh, well, you know, but that's just the Schrödinger representation. And quantum mechanics is much broader than that. There's much more in quantum mechanics than just the Schrödinger representation. And a lot of the discussion about interpretation of quantum mechanics, however, almost all of it, I think, has been limited to the Schrödinger view. We actually have two interpretations of quantum mechanics based around the idea that the Schrödinger equation, if you take the Schrödinger equation as the description of reality, two interpretations which don't have collapse. You know, so the reason collapse is not a problem is because in Bohm's theory there's no collapse, and in the many worlds theory there's no collapse. So it very much is a non-problem in those two interpretations. And I think it's, you know, I think this idea of taking a totally different algebraic view, you know, is one that has been, you know, in terms of interpretation of quantum theory, has been pretty much ignored, even more so than Bohm's theory, since the beginning of quantum mechanics, even though, you know, certainly from Heisenberg's point of view, that played a vital role in the whole genesis of the theory and the more general transformation theory. So it's very important that, you know, that side of the interpretation debate gets an airing and gets to be understood better.
Could I just make a philosophical? Can you hear me?
Yeah.
Just say something quickly.
Sure, sure.
This is just a philosophical curiosity that may relate to this, what we're now talking about, and may not. So if I accept that mind and matter are not separate, the question for me then is, yes, they may not be separate, but they may be different. And difference does not imply separation. So what I wonder is the deterministic element not operating in the mind dimension, but is operating in the matter dimension?
Would anyone want to try and?
Yeah, I'd get some quotes from Grassmann, who was a great mathematician at the turn of the last century, ages ago. And he said mathematics was not about material process, but it was about thought. How you order ideas in thought, how you order structures in thought. So that, I think, begins to bring together the mind and matter in a very interesting way. But that's not very popular out there. But that goes back to Grassman.
Well, thank you, Eddie, for asking that question. Thank you, Basil, for answering it. I believe that Shantana has his hand raised. I'll just unmute you. There you go.
Thank you. Yes. About the issue of the collapse of the wave function and its reality or non-reality, absolutely convinced it's non-reality. It's a false problem, and there are various ways of looking at it. And as Chris has mentioned, Bohm is one, and many word is one. I would add that decoherence is one, and it's probably the one that has most weight in current discussions. I could even add my own version of decoherence to that as being philosophically more fundamental. But the key fact is like quantum mechanics. If we understand quantum mechanics as a statistical theory, as I think we should, the big mystery remains the individual result, not the statistics. One can prove very easily that you don't need the wave function collapse to have a coherent, discrete, statistical description of quantum mechanics. The real puzzle, and I think most philosophically interesting and challenging puzzle, is if nothing determines what happens in one single instance, in one single result, where does that come from? Or does that have anything to do with us, with consciousness? Or I would say that's the real mystery of quantum mechanics.
Would you like to try an answer to that, Basil?
Or was it a question? I thought it was Santana giving his ideas. I think it actually comes from the very basic notion of what is movement. That what we try to say with movement is that the position, I'm going back to Zeno, I'm sorry. I'm an old man. And I don't think we've answered that problem properly. I think you have to have an ambiguity in your description in order to get movement at all. And therefore, Shantina, you're right. It's not basically in us. It's basically in the whole process of what we mean by movement. And therefore, we are trying to pin it down, and it won't be pinned down for the very reasons that Zeno gave us with the arrow. How can the arrow be at a point and yet moving at the same time? And I think quantum theory is actually telling us that the answer is in the ambiguity of, it's where the uncertainty principle comes from in the first place. That you cannot specify precisely the position and momentum of a particle or of anything which is moving.
Well, another way to formulate it would be, there's no contradiction between quantum mechanics and a philosophical notion of, let's say, universal consciousness. The real trouble is understanding individual consciousness.
Oh, sorry, I'm not attempting to solve consciousness when I gave you my answer.
Sorry?
I don't think it's a tremendous
No,
leap for me.
I wasn't referring to Dino.
Oh, sorry, I thought you were.
Well, that's the hard problem, isn't it?
That's the very,
The hard problem.
that's the very, very hard problem.
Yeah. Well, I don't think quantum mechanics will solve it any more than Newtonian mechanics will solve it.
No.
Now we are approaching the end, but I know there's so many questions still to come, and unfortunately I can't allow to answer all of them purely because of time. There is one thing though that has come up in the comments section, which is basically for the non-physicist. If someone could very briefly explain what a configuration space is.
Well, you know, it is a difficult concept. It's one that Paul and I certainly talked about quite a lot as to how to get this over in the film. And I think one of the problems is that the minute you say to people space, they immediately think of the space we live in 3 dimensions, X, Y, and Z. And I remember this even from my own youth when first learning about spaces which have more than 3 dimensions. I thought, well, how can you have a space which has more than 3 dimensions? Look, it's only got 3. And, so what is configuration space? We see in our real space, we have an X, a Y, and a Z, which tells you a location in that space. But if you have a configuration space, you want to have a space which has as many axes, well, I guess 3 times as many axes as you have particles. So a single point in a configuration space would tell you where all the particles are. So simply, if you had just 2 particles, in order to specify the position of one particle, you have to give its X, Y, and Z coordinates. So you could say X1, Y1, Z1. And if you then also want to specify where the second particle is, you have to then give it a second set of coordinates, X2, Y2, Z2. So 3 numbers tell you where this particle is. There's 3 numbers that tell you where this particle is. Okay, and what you do is you create an abstract space which has, instead of the 3 dimensions of space, it has 6 dimensions, okay? And a single point in that configuration space tells you the configuration of the system. It tells you where your 2 particles are. So it's a space which describes the configuration of a system of more than 1 particle, a complex system. It's a space in which a single point in this space gives you the configuration of your whole system. And that's what the Schrödinger equation controls. It controls how this wave function evolves. So it tells you what the Schrödinger equation is telling you is how the configuration of your system evolves in time. And so, you know, it's almost a literal thing. Configuration space is a space which tells you what the configuration of your system is. It's not to be confused with real space. It, you know, it's beyond, that's if you like, an abstract space. Although there's been some debate recently about whether you could, does it make any sense to say that configuration space is the real space, and that, you know, our everyday 3D space is just something which evolves from the configuration space. So it's almost an illusion. You know, the reality is in the configuration space, and we live in this this matrix.
So is it a case then, Chris, and sorry, James, I just have to get this question in. Is it a case then that configuration space could be interpreted as non-local?
Yes, well, the actual configuration, everything that happens in the configuration space happens locally, actually. So if you're at this point in configuration space, all that matters is the point you're at and the wave function around that point. So it's local in configuration space, but when you project out from the configuration space into our everyday space, it's the non-locality arises from this motion in the configuration space. So I don't want to, so the fact that you're at this point in configuration space tells you which of your particles are connected, and the wave function in that space tells you what the real relations are between your particles in the real space. Okay, so the non-locality is a consequence of the fact that we have to describe everything in configuration space. So right, the non-locality comes from the configuration space description, yeah.
Great, thank you, everyone. I do really apologize for everyone who wanted to ask a question but couldn't, but unfortunately time is running out. So just to close the session, Chris, would you like to say something just to close?
Well, I'd like to say thanks to everybody for coming along on the session, and also it's been very enjoyable talking to everybody and in the breakout rooms both today and yesterday, and I'll continue with this. I think Basil has some very interesting points which take a very different approach, going beyond this whole wave function configuration space story. I've certainly just confined my talk to that, and indeed a lot of the discussion about interpretation of quantum mechanics, perhaps wrongly, is all couched in those terms of wave functions and collapse of the wave functions. But for me, it was absolutely amazing when I first really looked into Bohm's theory and all that stuff. I've been reading about in the quantum theory textbooks, and all these strange, paradoxical, weird things that quantum mechanics was telling us, just evaporated in Bohm's version of the Schrödinger theory. And that all of these, these crazy ideas were just dispelled. There was no wave packet collapse. Quantum tunneling took place in a perfectly understandable way. The quantum world was a well-defined world in Bohm's theory, where things happen, for a reason, and there was no inherent randomness in this view. And this just went totally against everything that you'd heard already from your quantum mechanics lecturers. And I always used to say that, one of the greatest values, I think, of Bohm's theory is the fact that when someone says, in a debate about the interpretation of quantum theory, well, quantum theory proves that or shows us that X, you can then go and work that out in Bohm's theory. And if it's not there, you can just say to that person, well, no, quantum theory doesn't say that. You're saying that. You're bringing that into the quantum theory, because if it's not in Bohm's theory, then it is not part of quantum theory. It's something you've brought in. So if you say, for example, that consciousness causes the collapse of the wave function, quantum mechanics has proved that to be the case, you can say, well, no, it hasn't, because that doesn't happen in Bohm's theory. And to me, it's a bit like a touchstone that you can always work out in Bohm's Schrödinger theory how things work out, and it's a touchstone that will tell you whether whatever's being claimed is really part of quantum mechanics or part of something which is brought into quantum mechanics due to some predilection for some particular idea. So it's a wonderful theory from that point alone. I think I stop there, yeah.
Great, thank you so much, Chris, for joining us today and being part of our series. Thank you for everyone for joining. Thank you everyone for contributing to this session. It's been a really fantastic session. Now, just before we go, I do have, our usual announcements. First of all, I would like to invite you all to next week's sessions. Got two very exciting sessions. The first one is with Basil Hiley, who's here with us today, who will hold this session on Saturday, who will try to answer the question, how does the classical world emerge from the implicate order? And then on Sunday, we have something a little bit different, but I think you'll love it, which is Shantena Augusto Sabadini, who was here with us today, who will be talking about Lao Tzu and the implicate order, wholeness in Taoism and quantum physics. So for more information on these, I'm just gonna attach the links to their talks in the chat section. There we go. Second of all, I would just like to remind everyone that the recordings for the previous sessions are available. We do have them recorded, and even future sessions will be available for everyone who got their ticket. The sessions will be available about 3 days after they happened. So Saturdays will be available on Tuesday, Sundays will be available on Wednesday. If you have any other questions regarding the summer school or any other queries that you may have of any nature, just email us at the at our email addresses, which I've just put in the chat section, or just visit our website and we have a contact page. And I think that is it. Thank you again so much for joining us, and we'll see you again soon here at the Pari Center.
Thank you, everybody. Thank you, Fred. Thank you so much.
Thank you.
Thank you, everyone.
Thank you, everyone.
Thank you. Lovely to see you all.
Thanks, Paul.
Thank you so much.
Thank you.
Thank you.
Thank you.
Bye. Bye, Andrew. Bye, Yuriko.
Bye-bye.
Bye.
Bye-bye.
Salamat.
Bye, Stefan.
Stefan, bye.
Alan. Bye, Tom.
Bye,
Bye,
Tom.
Eleanor. Good to see you there.
Good to see you too, Tom.
Thank you very much.
Yeah, great.
Thank you. Bye-bye.
Bye, Patrick, Shantena, Dave, Shram, Caroline, Sky.
Bye-bye. Thank you very much.
Thank you all. Thank you all for joining us.
Yeah, wonderful.
Bye.
Take care.
See you
Bye-bye.
soon.
Take care.
Bye, Peter. Bye.
Bye. Bye-bye.
Bye-bye.